Hello, my name is Aaron Balke, and today I wanted to break down my Master's of Science in Data Analytics Capstone. I got my Master's earlier this week, and I want to break down my Master's Capstone in order to show both a technical breakdown of what occurred, and also I will include the executive presentation, which is supposed to be not as technical, but more for business shareholders, that sort of a situation. So that will be in the second half of this presentation. But the first part will be the technical bit. So let me open up the analysis. So for this capstone, what I am interested in checking out is regional energy consumption in the Northeast. And what we're going to be looking at is the PGM energy consumption data set. PGM is a regional transmission organization, and what they do is they control between a bunch of different states and a bunch of different localities, the connections, the energy consumption between those connections. And so they're able to see for Delaware, Illinois, Indiana, Kentucky, Maryland, Michigan, New Jersey, North Carolina, Ohio, Pennsylvania, Tennessee, Virginia, West Virginia, and DC, the energy consumption of those areas. And so what I want to check out is if the different regions, using paired t-testing, if the different regions have significantly different consumption patterns, because if so, then there's something, maybe climate, maybe lifestyle changes between different states. There may be stuff different between those different regions that we have to take into account when it comes to forecasting the future energy consumption. And so that's the first part, is comparing the different regions using paired t-testing. And then the second portion of the capstone is using that data and that analysis to then do time series forecasting of future energy consumption. And so we're provided with data between 2002 and 2018 for western and eastern regions of the PGM grid. The eastern regions are all of the states that are along the coast. So we're talking Delaware, Maryland, the east side of Virginia that's actually on the coast. And so those are the states that are involved in there. And then the western portion is all the other states. So we're talking Kentucky, Tennessee, Illinois, all those bad boys. And this data comes from Kaggle, but PGM originally posted it on their website. I believe it's a regulatory reason, but they have to post the hourly consumption on their website. And so the Kaggle dataset is just that original data, but packaged very nicely for data analysis for guys like me. So that's where the data came from and all. For this analysis, the null hypothesis is that the difference between PGM regional max energy consumption is not statistically significant. So the null hypothesis is that the difference between western and eastern PGM regions is not statistically significant. The regions have very similar seasonality, very similar trends, all of that good stuff. The alternative hypothesis is the opposite, that there is a difference between the regional max energy consumption between the regions. And I chose a paired t-test. Part of the capstone was we had to use 8 specific statistical methods in the analysis. Paired t-testing was one of them. And that will allow us to evaluate if the difference between those regions is statistically significant. And we'll be able to do that by comparing the mean values of the different regions. And that will be done without removing seasonal components, without removing trends, because that is data we want to compare between the regions. So we are going to want to remove stationarity from the dataset, but the seasonal and trend components we're not going to want to remove, because if there's a trend happening in the western region that isn't happening in the eastern, we want to be able to compare those aspects. So When it comes to the collection of the data, as I had mentioned, it's cleaned up and put on Kaggle. I believe the original data it was something like the PGM had hourly data down to I think there was 4 significant digits of megawatts, which is excessive in our situation because we're going to be comparing over a decade worth of data. So we did not need that hourly down to 4 significant digits. We did not need to worry about that. So luckily, the Kaggle version already rounded it to the nearest megawatt per hour. And when we do our analysis, we are going to be then aggregating it even more. We're going to be aggregating it down to the day, the max value every day, and then we're going to be getting the max value for each month as well when it comes to the paired t-testing. And so there's a lot of data here originally. I believe it was originally almost 300,000 records. And so we aggregate it a bunch down in order to get it down to be just the max monthly values for the paired t-testing. And the reason for that is there's a lot of randomness involved in energy consumption. And so if we keep in each hour's little blips and blops in there, we're going to have so much random noise in our data set, it's going to be impossible to actually run a analysis on that data. So that's what all the aggregation is for. One major advantage of using the Kaggle dataset is that we have the aggregated data and all already down to and the rounded data. It also cleans it up and makes it much easier to use, but the one disadvantage is that we have to be concerned about the integrity of the data because it's not coming from the original source, it's coming from a third party. And so I did have to go through and I did some comparisons of the data in the Kaggle dataset versus the data in PGM's actual website and their database. Luckily, all checked out, all the amounts that I checked were correct, and the same between PGM and the Kaggle version. So based on that, we can assume that the data has integrity and is intact. Yeah, so that's the data collection process. When it comes to data extraction and preparation, so I guess we can break down the tools first. The programming language we're going to be using is Python version 3.10. Python's chosen because I am very comfortable with Python. I would be scared to do my analysis in R, so we ran it with Python. And luckily, there's a lot of community support in Python for data analysis. Additionally, we're using a Jupyter Notebook environment. The reason for using a Jupyter Notebook environment is mostly the checkpoint functionality. We do not want to be running these models over and over again, especially since we have 2 portions of our analysis. You wouldn't want to run the paired t-testing every time you want to do the time series analysis, so we want to be able to split into little chunks and run those aspects over again if we need to, or save the state of those little chunks and not have to run compute intensive modeling over and over again if we don't have to. We run in pandas. Pandas data frames are amazing. NumPy is being used for mostly for their operations. The aggregation is completed using pandas data frames, but under the hood, those are just aggregations done with NumPy arrays. And so NumPy is going to be very useful for this analysis. We're also using stats models. Stats models is being used because it provides the paired t-testing and Dickey-Fuller test. There's a lot of analysis functions that are automated through the use of stats models. And those are the tools we got. When it comes to the steps and techniques, the first thing we got to do is set up the environment. And so first thing we got to do is install the TBATS time series analysis package. TBATS is a special kind of time series analysis that's really useful for complex seasonality, and I'll get into more of that later, but just know we're going to need to install a version from GitHub in order to do that. So that's what we got going on here. We got all the standard imports, pandas, numpy, pyplot, so we import those as well. The next aspect will be the t-testing and normality imports. This is for the paired t-testing, and so we get SciPy stats and the stats models imports in there in order to do those paired t-testing analysis aspects. For the time series stuff, we're going to be importing from stats models as well. We got to import the Dickey-Fuller test, add Fuller here. Seasonal decomposition allows us to take out the, split it into different aspects, the seasonal component, the trend component, and the residuals as well. So that's what we got going on there. And then the plot ACF and PACF will allow us to see the seasonality and actually see the seasonal cycle. Next thing we got here is the mean squared error. That's going to be used to see how good our time series analysis is at the very end. Then we got to set the random seed as always, just to make sure we can remove as much randomness as humanly possible. And then we import the data. So we're importing from Kaggle. It had the western and eastern portions on different CSVs, and so we import both of those and have two separate data frames for that data. Then we got a lot of fun here. This is just data preparation here. We're renaming columns because particularly naming things megawatt isn't going to make a lot of sense when we aggregate it down to, we're aggregating hourly data into monthly data, because having megawatt values there is just going to be such a mess. So we stopped calling it megawatt in the column names, and at the very end we do convert it to gigawatts, just so we have a number that makes sense. Having thousands of megawatts, it becomes a lot harder to think through, so we gotta convert to gigawatts there. Part of the fun with time series, as always, is getting the time information parsed from strings or from a different value. And so part of the fun here was just getting the correct date time value out of the data frames. And luckily, we were able to just do a standard formatting here, and that allowed us to then group all of the data by that date time. So if something had the same date time, we combined it and used the max value, so aggregation there, we group by the date time value. So if you had multiple values for each hour, then we just took the biggest one. The reason this occurred was in a energy grid, you have multiple points along that energy grid that you record the energy consumption. So we just wanted the biggest one, because what we're interested in is the max energy consumption in order to plan for equipment failures, equipment repairs, all of that good stuff. Next thing I did was I set a start date for the eastern and western portions. They did not start at the same time, so the eastern portion started on January 1st, while the western started on April 1st. I'm assuming this probably came down to some regulatory thing, so we had to set separate start dates. And in order to deal with the date-time mess that time series analysis always has, I decided, since every value, every hour and every hour had a value, to just add an index, since they were already in order and there were no missing values. That's the only reason this worked, but I just added an index, and then using the start date, I then just added the index value to that start date. So I just incremented through the different columns, since I knew they were all in order and there were no missing values. Though that's the only reason this worked, but that's how we got this new date feature to add to the data set. Since we had this new correct date feature, I removed the old date time feature and set the index to our new date feature. This new date feature is set to the index, since doing that with a data frame allows much easier time series analysis in the future. A lot of stuff gets automated with those Adfuller or Dickey-Fuller testing and the decomposition of the seasonal trend and residual components. It all becomes a lot easier to do if you set the index to the date field. And the last thing I did was remove the last date from the data frame, because the last date, they always, it must be UTC versus East Coast time. They always cut off not right at the end of the date. And so I just removed the last date so we didn't have any days with without a complete set of 24-hour values. And then this was gigawatts, just saying the data frame there. So now that we got the two data frames made, what we did next was I just cut it down to be a decade's worth of data. And the reason for that is they had separate start dates, and we do need the same sized data frames for the analysis, the paired t-testing analysis. And I figured 10 years was more than enough, and anything else, if we can't tell if they're the same using 10 years, we got big problems. So we did that here, and we can see the shape is equal. Then I concatenate it into one data frame using both the east and west data. This will use the date as the index and then just have the energy consumption of both regions right next to each other. I then remove the extra index column there, just so we don't have to deal with that anymore. Then we go on to preparing for the actual paired t-test. So the paired t-test is going to require, first off, stationary data. When you're doing a paired t-test with time series data, you have to make sure it's stationary first. That's pretty standard with all time series analysis, but it's important to note that we do have to do that for the paired t-testing as well. So we're going to be running Dickey-Fuller tests. We are going to need to check for normality and outliers as well. And then if the data is not normal, we do have to do data transformations to get it to be normal before we do the paired t-testing. So first thing I did was I resampled the data to be monthly instead of daily or hourly, and I just take the max value for each month. And so we take all of those hourly values for that month and then say what's the highest. That's what we need to compare between the regions. So we do that and reset the index just to make it happy. And then we have the Dickey-Fuller test. We run it on both the PGM East and PGM West data. What we get back is neither data sets are stationary. So both of these have a p-value greater than 0.05, which is our alpha value. For all of this analysis, our alpha value is 0.05, so we can be 95% certain if the data is stationary or not, and future analysis 95% certain of things. So we know the data is not stationary. In order to make it stationary, we run difference on it in order to reset it, and then we drop NaN values in order to remove, since we're getting the difference between values, there will always be one empty value at the very top, which we remove from the data set. Then we run stationarity testing again using a Dickey-Fuller test, and we see it is stationary. It isn't exactly 0.0, but I just round the values because I wanted it to look a lot better than having some scientific notation that just goes on for a bunch of values. So that's what's happening there. But data is stationary at this point. Now, in order to do a paired t-test, you need outliers and normality, outliers removed, and the data to be normally distributed. In a normal t-test, you would do this on the data itself, but since we're doing a paired t-test, we have to apply this to the difference between the regions we are comparing. And so we have to get the difference value first. So we get the difference between the eastern and western regions' energy consumption. So what's the difference between those two values? The max monthly energy consumption values for those two regions, get the difference between that, and that is our data that we have to remove outliers from and check for normality with. So, first thing we're going to do is visually check for outliers. And as we can see, there are a few outliers, and so we're going to remove those. And my method for removing them in this situation is using z-scores. I used the standard z-score of anything greater than 3, remove that from the data set, which is what I did. It is kind of funny that the graph looks identical even with them removed. I think there's one or two at the very top that has disappeared from the outliers, but I just used the standard z-score of 3 just to remove the outliers that are really far off in the distance. So we have outliers removed here. Now we need to check for normal distributions. I am using a D'Agostino-Pearson test for the normality test. And as we can see, it's fairly close to being normally distributed. When we did the normality test, we got back a p-value of 0.043. In our situation, we're wanting it to be higher than our alpha value of 0.05. So that means that using this normality test, we are not normally distributed. We're very close to being at that greater than 0.05 value, but we do need to do some data transformations in order to get the data to be normally distributed. I decided to use a Yeo-Johnson normal distribution, and the reason for this is since we are using the difference value instead of the actual values, that means we do have negative values sometimes. Sometimes we have in the difference values, sometimes we have negative values. And one of the complications with data transformations is that our transformations, there's some transformations that cannot be applied to data with negative values. And so we need to do some form of data transformation in order to get a less shallow normal distribution. And in order to do that, the only real options we have are Box-Cox and Yeo-Johnson. The one complication with Box-Cox, though, is that that requires all positive values. So that only gave us the Yeo-Johnson option. So we run that, we get the max lambda value, that's the equation that we're putting in for the Yeo-Johnson. I just automated it for myself, and then we got back the transform data, and then we run our normal normality D'Agostino-Pearson test on it, and we get back a p-value of 0.068, which means now we are normally distributed. So it's a bit hard to tell. The graphs look very similar, but if you take a look at this, let me see if I could get it on screen. There we go. All right, there we go. So if you take a look, the only real one you can tell with is this one between, the one just on the left of the 0 line. We can see that is much bigger in the second one, so more stuff is centered on the normal distribution. So now that we ran that and got the normal, now that we have the difference data normally distributed, we have to apply those data transformations to the original data, not the difference data, because we're going to now put the original data into the paired t-test after it's been transformed. That way the the paired t-test is being applied on normally distributed data. So using the same calculation, the same Yeo-Johnson, we just get a clean Eastern and Western sets of data for the paired t-test. So, pair t-testing. The pair t-testing is actually the hardest part is doing all of the data preparation and doing everything we mentioned previously. The actual pair t-test is pretty simple. We just put the clean Eastern and Western data sets that we're going to compare in and get out a p-value. The paired t-test uses we're going to use a alpha value of 0.05, and the p-value we want to have, if it's above that alpha value, then we know the two groups are not statistically significantly statistically different, and if it's under, then we know it is. So we throw in the data into the paired t-test, and we get back a p-value of 0.065. That means we can conclude the two groups are not significantly different. And if there's any perceived differences between the two groups, then we can just call that random variation. We don't have to compare these two groups, or we don't have to look at these two groups as different on a statistical level. And from a practical perspective, this means seasonal components are shared between the two, so there isn't that big of a difference when it comes to energy consumption on the coast and on the not mainland, in country. There's not that big of a difference between those two groups when it comes to seasonal energy consumption. So the increase in energy consumption if you're on the coast in, let's say, the summer is the same as it would be in the country, and like in the winter it would be similar as well. And in order to really push this idea home, I did decide to make a scale adjusted comparison graph between the Western and Eastern groups, and that is what we've got here. The orange line here is the max energy load for the Eastern region, and the Western region is the blue. And as you can see, those two values sit very close to each other and move up and down right on top of each other. Very little variation between the two groups. So we really know that these two groups are not significantly different when it comes to energy consumption, and we are able to, for time series analysis, combine them and run our analysis on both of them at the same time, because we know the modeling will be identical, or at least very, very close to each other. We're not going to have significant differences in forecasting future energy consumption between regions. And that is the next step. Now that we got the paired t-testing done, we're going to do TBATS time series analysis. And so first thing we're going to do is we're going to combine those data sets into one combined energy consumption value for PGM, a combination of both the Eastern and Western regions. And then we're going to drop data or features we don't need anymore, which is the index and the original Eastern and Western regional energy consumption values. And one aspect of this time series analysis that I'm sure has probably been brought up already, like something you've probably already noticed, is the TBATS time series analysis. Originally, when this analysis was being done, the plan was to use a ARIMA ceramics modeling. ARIMA is just the standard when it comes to time series analysis, the most basic kind of time series analysis. And so that got started. And as we will see when it comes to the autocorrelation in order to check the seasonality of the data set, we had problems where the seasonal component, there were two seasonal components. And the problem is ARIMA modeling is not able to handle a complex seasonality, multi-seasonality. And so I had to find a solution for time series analysis that would allow us to do multi-seasonal complex time series analysis. and the answer was TBATS, time series analysis. TBATS is a combination of multiple different time series analysis aspects and methods in order to create a model that is able to model complex seasonal components. So we'll get into that and the technical aspect of that a little bit later on. But just know when we're going through this that it's originally planned to use a ARIMA model, but ended up being a TBATS model. So the data is combined, as I had mentioned previously, and then we get back just daily values. For the paired t-testing, we did use monthly aggregations and grouped by month. For the time series analysis, we are going to use days because it's not necessary to aggregate that much for this analysis. First thing we do is check out the observed data. As we can see, there is something seasonal happening. So we're going to have to look further into the seasonal components because it's very obvious something is happening when it comes to seasonality. First thing, as always, when it comes to time series analysis is running a Dickey-Fuller test to check for stationarity. The combined data set does come out to be stationary, so we have a p-value of effectively 0 here. So we don't have to run difference on the data set. Next thing we do is decompose the time series data, and so we split it into both a observed, seasonal, residual, and trend component. For this visualization, I did make sure to have the same y-axis, and the reason for that is just so we can see what is happening, the magnitudes of the different components, because in this situation we can see this seasonal component is significantly smaller than in magnitude than our trend component, which you probably can see it already. You can see that there appears to also be a seasonal component in the trend component, which we will get to soon, but got the same y-axis in order to compare magnitudes. And residuals are there as well. So in order to get the seasonal components and the period of the seasonal components, we have to use autocorrelation. The autocorrelation is applied on the seasonal component first, and this allows us to see, with autocorrelation, the seasonal component would be seen by when we have a correlation coefficient of 1. And so these are each day, each value for each day, and as we can see, on the 0th day, we have a value of 1, a correlation coefficient. On the 7th day, we have a correlation coefficient of 1. So we can assume from that, and as you can see on the 14th there's 1 as well, so we know that there is a seasonal component that is of 7 days. So we know there is a weekly seasonal component. Now, as I had mentioned, when you look at the trend component, there's obviously something seasonal happening there as well. So I ran autocorrelation on the observed data as well, the original data, without being decomposed. And what we get back is there is something going on with a correlation coefficient. We got the 0th day, and then we see it's not completely all the way up to 1 on the 180th day or on the 360th day, but we're talking roughly, we're getting big jumps beyond just the standard beyond just the standard observed data. So what we know is something is happening with the observed data where we have a seasonality of a year and something, a little blip going on about halfway through the year. So we know there is a seasonal component in addition to the weekly seasonal component, one that is an annual seasonal component. And as I had mentioned, a ARIMA model would not be able to model this effectively. When I did try using a ARIMA model, the line was terrible. It just went straight across, which was not what we wanted and was not effective at modeling the data. So we had to use a TBATS modeling. Before falling on the TBATS modeling solution, I did see that I could use Fourier terms and trigonometry functions and do those sorts of data transformations before using a ARIMA model. However, that became a massive mess for me with periodic functions and all that fun stuff. So I looked for the other option, which was TBATS, which would automate the entire process. So that's how I came to TBATS modeling. And TBATS modeling, it's a abbreviation for trigonometric seasonality, Box-Cox transformations, ARMA errors, trend components, and seasonal components. And so the combination of these, the way TBATS works is it goes through all of these different modeling methods and combines them and manually goes through each option and does different combinations of all of them to try to find the one with the lowest either AIC value or BIC value. And so it goes through and goes and runs every option and every combination it can until it finds one that works the best version. And this was originally described in 2011, and the Python version I am using was created in 2018 for this analysis. So, for the time series analysis, now that we know what we need to do, now that we know we need a TBATS model, we have to first create a training and test split, and I decided to use a split that was 2 years of testing and the rest of the data as training, so the other 8 years as training. That's not a perfect 75-25 split, but I figured 80% in order to maintain yearly chunks was worth it. So that's why we're using a 2 out of 10 year split. So that's what we got going on here. We can see the testing data is marked in orange and the training data is in blue. For the TBATS analysis, luckily that package from GitHub does all of the hard work. We just have to put in what the seasonal components are. So we have a weekly component, so 7 days, and then the month or yearly component, which is 365.25. So we put that into the TBATS modeling object and get back out an estimator. Then we just fit our training data to that estimator to get back a fitted model. Then we run a forecast on that model equal to the test data. So we do 730, 2 years, and we also want to get out a confidence level of 95% for our forecast. So we get back out that forecasted data and confidence interval. The one downside of this TBATS model from GitHub is that it does not output it as a nice data frame. You have to go through and manually set everything and convert the forecast and the confidence intervals to be data frames for easy use and visualization. So that's what we got going on here. And then we just plot the forecasted data against the test data and the observed data, and it looks pretty good here, and it is pretty good, but it's just hard to see here. So I did also just show the test versus predicted data with the 95% confidence interval, which is here. Now, I was very happy to see this. We can see that the annual component is being forecasted very effectively. So we got the annual annual seasonal component being shown here, and we also, it might be a bit hard. Okay, you can see that it also has the weekly seasonal component in there as well. So the different seasonal components are matching the model and being fitted properly. I did print a summary here, so we are able to see that Box-Cox transformations were included in there. There's a trend in there, the seasonal component, the harmonics of it. We're able to see there is no ARMA errors in there, and there is a bit of a trend as well in there. So that's just some extra numbers, and if you need to troubleshoot something, you can check out. In order to evaluate this time series analysis, I did make data frames of the residuals in order to run the different metrics. So we got the MAE, the mean absolute error, and percentage error. We got those in there. And the percentage error I included for a business context. I feel like if you were in a business context in a executive meeting, it would be really useful to just say a percentage as opposed to absolute intervals and absolute energy consumption values, because I'm sure that can get lost in explaining stuff. I also included a mean squared error in here. And so when we get all that stuff back out, we're able to see our mean absolute percentage error was 7.67%, and our RMSE, our root mean squared error, is 4.61 gigawatts. So those two are the main metrics I care about. We're able to say that our model can predict with only a 7 to 8% error the forecast of future energy consumption, max energy consumption for the PGM energy grid. The RMSE value is useful because we're here able to say that on average we're only off by 4.61 gigawatts. So at any time we're averaging that much of an error, which being able to know how much of an error we're off by, we're able to see and plan on that when it comes to maintenance, when it comes to repairs, and all of that good stuff. So, as we saw, the paired t-testing showed us that the regions are not statistically different, and so we were able to forecast based on the combined data. The time series analysis created a TBATS model that was capable of forecasting with only a 7.67% error and only being off an average of 4.61 gigawatts in max energy consumption for the entirety of the PGM data or PGM energy grid. I do think it's important to mention one major limitation. The biggest limitation was that when it came to the paired t-testing, using time series data is very spotty. You have to be within a very narrow margin in order for it to work. And so I did a lot of wrestling with the stationarity of the data, because if I made changes to make it stationary, I would have problems when it came to the normality test, where I could not transform the data to be normally distributed accurately. And this was all involved with aggregating the data. If I made the aggregation too big, it wouldn't work. If I made it too small, if I used yearly versus monthly versus daily values, those different aggregations could cause problems when it came to the stationarity, when it came to the normal testing. And so you have to be very careful when you're doing paired t-testing on time series data to get the margins perfectly, in a point where you could even do a paired t-test. And so once I was able to do that, the analysis was perfectly fine at that point. But if you're doing paired t-testing on time series data in the future, be sure that you choose the correct aggregation, and that can take a lot of trial and error. Since we were able to create a time series model that was able to check for or model and forecast future energy consumption, I think the next course of action will be for PGM to diagnose grid equipment to make sure it can meet those max energy loads. And one nice thing about this analysis is we have the predicted values, which is this red line here, and then we also have the upper bounds of the 95% confidence value. And I'm not an expert when it comes to energy, the values that equipment can handle, but as you know, from a big overview perspective, my assumption would be we want to get at least to the point that the entire grid can handle this red line that of predicted values, and then sort of best case scenario, we want to try to get our equipment to handle this upper bound of the 95% confidence interval, because if we're able to get to that point, there are very few days in the year that go anywhere near that 95% confidence interval upper bound. And so if we're able to get our equipment to handle that, then we won't ever have any sort of equipment failures, any sort of penalties from failing to provide energy to our clients. So that would be my what I would assume would be the ideal course of action. It is important to note, if we are doing this analysis January 1st, that gives us a good 7-8 months to do executive decision making, doing project management, in order to have a grid that can handle the highest energy consumption values of the year. So in July and August, we have our high, our summer peak. And so we have 7 or 8 months in order to plan and get things moved around, get things working properly before we have our big jump up in energy consumption. And then when it comes to future analysis and possible studying on this data set in the future, I could see that while we didn't find it using paired t-testing in this situation between PJM West and East, I could see how more extreme differences in climate could make a big difference in energy consumption. So maybe it would be worthwhile to compare PJM's data to another regional operating group, such as I wouldn't know the name, but maybe like a Florida energy grid, and compare and see if they have, using paired t-testing, a massive difference in energy consumption. Or maybe Washington, maybe the Pacific Coast has different energy consumption seasonally than the East Coast. So comparing more extreme regions to see if there's a major difference, and see if there's a major difference between those more extreme regions. The other thing I think would be worthwhile on this data set in particular would be to use machine learning to detect anomalies in the data set. There are moments where there are major drops or spikes in energy consumption, as we can see in 2011, the June, July, and August. We can see these massive peaks. Why did those anomalies take place? What was happening around that time? Again, we can probably assume some sort of climate variation, but using machine learning, we would be able to make more informed decisions, and we may be able to check for indications of future major equipment failure, energy theft, and other problems. So using machine learning, we may be able to make more informed decisions moving forward in equipment maintenance and all. That is the technical breakdown of my master's capstone. I hope you enjoyed. The next aspect will be a breakdown for the non-technical audience, for more of a business and executive presentation. So I look forward to that. And if you are interested in checking out the GitHub, there's also all of my write-ups for this. There's about 2 or 3 write-ups for this capstone as well. And thank you. Hello, my name is Aaron Balke, and today's video is going to be my non-technical capstone presentation. For my capstone, I am comparing and forecasting PJM regional energy consumption. PJM is I believe the technical term, the technical acronym is RTO, but they're a big conglomerate of smaller energy companies in the northeastern part of the United States, and so they control the interconnections between those different entities. So, I am going to be your presenter here. I have 10 years in the financial industry. I've worked as a tax preparer, I've worked as a accounting specialist, and done a little bit of financial planning here and there for people. And the main goal with all that financial work I've done in the past and just everything I like to do and hopefully into the future is I want to know how data affects people. How can we take data? How can we provide benefits to people? How can we see where people are losing out on things, gaining things? How are we able to see how data affects people? And that leads into my BS in computer science, my bachelor's in computer science. That also is why I'm going to try and at least hopefully get my master's in data analytics as well. I really care deeply about figuring out how data affects people, and that's everything I've been working for. So, and hopefully with this presentation and this project, it's the same sort of thing. How can we see how data affects people? So, for our capstone, the problem is we need to know the max energy load on a power grid in order to evaluate equipment longevity and allocate resources effectively. We have if we are unable to figure out the max energy load on the power grid, then we won't be able to facilitate maintenance and repairs in a timely fashion in the correct places, and then we'll begin to have the power grid go down in places and regions, all that sort of stuff, which will be very detrimental for our customers, and the regulatory bodies will get involved, we'll lose business, we'll have to deal with those repairs at a terrible time, during a situation where everything's falling apart. So we want to try and forecast the max energy load of the power grid and the regions in order to not have those bad things happen. So for this capstone, the first portion will be to compare the regions to see if there is a significant difference in the max energy load between regions, because if there is, then we have to forecast those differently, each region separately. If there is not, then we just need to do one giant forecast. And the second part will be the actual forecasting of time series information and the future energy consumption. So those are the two parts of this analysis. And the hypothesis for this analysis is that the difference between PGM regional max energy consumption means is statistically significant. And so the hypothesis is that the western portion of PGM and the eastern do have significant differences in their energy consumption. It is important to note PGM West is everywhere from Illinois to Virginia to the edge of Virginia, including West Virginia. West Virginia is in there, only portions of Virginia though. And the PGM East is everything right on the East Coast. So you have Delaware, you have Maryland, you have New Jersey, and parts of the coast of Virginia there. So that sort of gives you an idea of the different regions that we're trying to compare in this analysis. The process for preparing this analysis. The first step is to make conversions. The data we were given was hourly data for a decade worth of hourly data, which is a lot of data. And so it was also it was a bunch of megawatt values, and when you start aggregating those all together, when you start combining them into monthly portions, we start to get these massive megawatt numbers that we just want to replace with gigawatts. So that took place, and then I mentioned a little bit the aggregation. We do want to take it from hourly data into monthly data, and the reason we want to do that is when we leave it as hourly data, that's a ton of extra data that we don't need for this analysis, and B, we start to include in some randomness, and there's a weekly seasonal component that gets added in there, and that starts to cause problems with the analysis. And so by aggregating it to months as opposed to hours, it's much easier to deal with and provides more value to our analysis. So that's the first step. Second step is to check for stationarity in the data. That's just making sure that there isn't any trends that are affecting the data. And then we got removing of outliers. We don't want anything really either positive or negative affecting the skew of our data. We really want to just deal with the normal distribution of data, the normal stuff. And speaking of which, we also have to do normal transformations in order to have a normal distribution, a requirement for our comparison analysis. And I've included two graphs here to show the normal distribution of the data. And so we're able to see, sure enough, everything is normally distributed before we put it into our comparison analysis. So, the findings of our comparison analysis. We take the eastern and western data and then we compare the two, and what we were able to get back out was that the regions are not significantly different. So that means we're able to conclude that they do share trend and seasonal components, or at least they're not significantly different, the ones that they do have. And just to really push that home, I have included a graph of the eastern and western data on top of each other. And so the orange values here are the max energy load in the eastern region, and the blue values here are the western region. And so what we're able to see is when you adjust the scales, these two data sets are sitting right on top of each other for the entire 10 years, and very rarely, very minimal differences from each other. So we are able to visually see visually confirm the conclusions of the analysis, that the regions are not significantly different. With the regions not being significantly different, what that means is we really don't need to do a separate forecasting model for each region moving forward, since there isn't a difference in the seasonality or the trends between the regions. When we do a time series forecast, we don't need to worry about doing those ones separately. We're able to combine the data together and make one single forecast model for the future. And that is the second step of this analysis. So let's see. Okay, I am not blocking it. The time series analysis that took place when we did some exploratory data analysis before we actually made the model, it came to our attention that there was a weekly and annual seasonality to the data. And so what that means is there's a cycle in the consumption throughout the week. So parts of the week have higher consumption than other parts of the week, and the same story is for the annual seasonality. And so parts of the year have higher consumption than others. And what we found, if I move my head, what we found was that we had a peak in the winter and a peak in the summer. And it can be assumed these peaks are based on climate control, and so you have heating in the winter and AC in the summer. The summer AC one was a higher peak, just a wee bit, but higher peak there as well. So we're able to see that there are two seasonal components to the data. Now, the complication with that is that does mean we're not able to use standard ARIMA models when it comes to modeling that, but we are able to use TBATS, which is a super special time series modeling way. And so we were able, by using that special TBATS modeling, to create an effective model of our multi-seasonal components and make a good forecast on future max load. And the forecast we were making, that we did make, was only off by about 5 gigawatts on average, and that came to around 7-8% error when it came to our forecast, which is really good. And so this top graph over here is the data, including the original data we used to train the model, which is the blue. And then I did a little zoom in on the training and predicting area at the bottom here, so that's a little bit easier to see. But we have the orange line here is the data we used to evaluate. That's the actual values for these 2 years we forecasted. The red line here is the predicted values, so that is what our model said the max energy consumption at this time would be. And then this pink area is the confidence interval. Our model is 95% sure that the actual data is going to be somewhere inside here. And so as you can see, we're able to keep it very close, at least get the major trends and seasonality of the data included in this model. There are some spots where the actual data goes up much higher, but something nice that I noticed, it's not really a normal evaluation technique, but what I kind of noticed was the confidence interval, the 95% confidence interval, keeps the high peaks of the actual data within it in most circumstances. And so the way I see it, we should aim to have the predicted values, this dark red line, as the place we need our equipment to be for sure. But then if we're trying to be hopeful, if we're trying to aim for the stars, we want to try to get this 95% confidence interval, the upper bound of this, as our best case scenario, because if we're able to reach to there, then we pretty much never have any instances of the actual data going beyond that. So that would be how I interpret the situation in respect to practically the business situation and what executives need to make decisions on, and dealing with equipment and all that sort of stuff. One major limitation with this analysis is that when it came to comparing the regions, we did need a very balanced set of circumstances in order for that to work. We had issues where if there were changes in the aggregation method, where we aggregated by month, if we used a different method, if we aggregated by day, by week, by year, we began to run into problems where there either wasn't enough data or too little data, which became a problem. And a similar problem was dealing with the time range. If we only did a year instead of the full 10 years, we would have similar problems where there just wouldn't have been enough data. And so trying to balance these out was a very delicate problem, and it led to a lot of trial and error. So a lot of this analysis was just getting this comparison to work, because we needed a very delicate set of circumstances in order for it to work. So that was the major limitation of this analysis. And for future courses of action, I would say first step will be to start looking at equipment and assessing the quality to make sure it can meet those predicted values, that red line I had talked about previously. We want to make sure for sure we're at that line. And then, like I said, if we want to be hopeful, if we, our reach for the stars business goal would be that 95% upper bound confidence interval. Because if we're able to meet that, then we very rarely will have circumstances that we go over that. And so if we're able to get to that point, then we won't have surprises where we no longer can deal with the consumption rate and equipment starts failing. We won't have issues where we won't be able to provide to customers and all. So, and then I did make a note that this analysis is taking place in January, and the big peak is in the summer, and so that gives us about 7 to 8 months to prepare for the next major summer peak. So we have 7 to 8 months as PGM to go make executive decisions, start working on project management, and actually get equipment replaced and repaired. So we have a time frame and a generalized business plan. So expected benefits. The thing that really brought this up was the Winter Storm Elliott in 2022. And the reason that was sort of the initial starting point for this analysis was, at that time, PGM got such terrible equipment failure, and it came up so unexpectedly, and we were very unprepared at PGM. And so that caused regulatory agencies to slap $2 billion in fines and penalties on PGM. And that is a absurd number that personally I cannot fathom. So if we're able to forecast and compare regions and forecast max energy load, that's going to help us to keep equipment from running into these situations like Winter Storm Elliott, and hopefully save us $2 billion in fines. It'll hopefully lower maintenance costs, because if we're doing preventative instead of curing of our equipment failures, that's going to be cheaper, and we also won't lose as much business if we don't have failures in the middle of winter storms. So and I did make a little note here: an ounce of prevention is worth a pound of cure. If we're able to fix these problems before they become big problems, then we're going to save a ton of money. We're going to be much better off as a company. And so that is the main point of this analysis. Hopefully this is a great starting point for future analysis to get better insights into further ways to deal with equipment and maintenance, all of that good stuff. And yeah, thank you for watching. I hope you have a good one.